In this video, we introduce our work, What Has Been Overlooked in Contrastive Source-Free Domain Adaptation, leveraging source-informed latent augmentation within neighborhood context. This is the outline of this video. First, we introduce the objective of our research. We aim to conduct theoretical analysis to investigate how variations in the design of positive keys in contrastive clustering can affect the performance of the source-free domain adaptation. Then, based on the insights we gathered from the theoretical analysis, we come up with a simple technique called source-informed latent augmented neighborhood to enhance the existing contrastive framework. In fact, our work is inspired by some observations. As you can see from the Disney visualizations of the target latent space, where we use the source pre-trained encoder to extract features from the target images. The domain shift actually introduces significant dispersions of those target features, which makes the source pre-trained classifiers hard to derive decision boundaries on those far target features. However, the neighboring target features still tend to belong to the same class, which means in the latent space, the features that share the same ground truth are much closer than the features share the different ground truths. Next, we talk about the literature review of our work. The problem that we wish to tackle is called source-free domain adaptation, where is a problem that we wish to adapt a model that is pre-trained on a source data domain to perform effectively on a new data domain called target domain without access to any source domain data during the target adaptation. Therefore, in this scenario, the target adaptation becomes an unsupervised learning problem where we are just giving a source pre-trained model and we wish to derive a classification model on a completely unlabeled target data. And one state-of-the-art performance framework to tackle this problem is to use contrastive learning. The effectiveness of the contrastive clustering is in fact heavily depends on how positive keys are defined. In general, there are two ways to define the positive keys for the contrastive clustering. The first way is to design a data augmentation technique and use the predictions of the target query samples augmentation as a positive key and use the other samples as the negative key to perform the clustering. And the second way is to use the neighborhood searching based method, which just simply use the predictions of the k-nearest neighbor of the target query sample. Next, we will talk about the theoretical analysis of our work. Our theoretical analysis is built upon a simple contrastive objective called influence CE. So for influence CE, the positive key are defined as the predictions of the transformations of the target query sample, and the negative keys are defined as the transformations of the query of the samples set within the same mini batch. And our proposition 1 demonstrates that the misalignment associated with two distinct alignment errors in predictions with respect to the positive key and the negative keys can be upper bounded by the contrastive learning objective, which means we can reduce the misalignment error by minimizing the contrastive loss. Next, we explore how we can reduce the target classification error in the contrastive source-free domain adaptation frameworks. Here are some preliminaries. So we define the samples predicted to be class Z can be enclosed within a ball of diameter delta. And based upon that, we define a subset of positive key within the ball as a SZ plus. And we also define a subset of negative key that are outside the ball as SZ minus. Then we reformulate the target classification arrow with respect to the misalignment arrow. And which can be demonstrated here is that the target classification arrow is equal to two terms. One term is with respect to the predictions of the target queries that are not belong to the cluster Z, and the second term is the the cluster Z is actually not equal to the current target query's ground truth. For more details with respect to the derivation of the new classification arrow can be found in our appendix of our paper. Therefore, a new upper bound for the target classification can be derived in our lemma 2. So for lemma 2, we demonstrate that the target classification arrow can be upper bounded by the sum of the three terms. The first term is the ratio that outside the ball defined by the diameter delta of the cluster. And the second term is that the probability that we misclassify the positive keys, which means the predictions of the positive key is actually not equal to the ground truth of the target query samples. And the third term is that we actually have the predictions of the negative key to be equal to the target query's ground truth. Those are two misalignment errors that we can find for the contrastive clustering. So based upon the lemma 2, we come up with the three oversights by the existing contrastive SFDA methods. The first oversight is that the data augmentation actually lacking the domain-specific insight that can misguide the model under the domain shift. In this case, the both misalignment error term can be increased. And the second oversight is that when we use the neighborhood searching method as a positive keys, when we expand the neighborhood searching range, which means we increase the number of k neighbors, can lead to smoother prediction, but also increase the risk of the overlapping regions between the clusters. And the third oversight is that we need to come up with the technique that can enhance the source pre-trained model's utility for the positive key. Therefore, we can decrease the transformation misclassification errors with respect to the second and third term of our. Next, we will introduce our simple strategies to address all three oversights, which we name it as the source-informed latent augmented neighborhood. So for this method, we first utilize the source pre-trained models to figure out the k-nearest neighbors of the target query samples. And then we use the source model, which is updated on the source data, to figure out the k-nearest neighbors of the target queries. And for the source-informed KNNs, we use the standard deviations to parameterize the Gaussian, zero mean Gaussians, and we sample noise from this Gaussian, and we add this noise into the latent features of the mean of the KNNs from the target models of the target query samples. So therefore, the info NCE loss with our source-informed latent augmented neighborhood augmentation can be defined as we use the positive key of the predictions from the augmented neighborhood as a positive key, and the augmented neighborhood of the other samples within the same mini batch will serve as a negative key. And next, we will explore the rationale behind our proposed CLAM. And first, in order to better understand the reasoning, let us first examine a general scenario in which we introduce a noise with the Gaussian, with the zero mean Gaussian of the standard deviation sigma to the curious latent neighborhood centroid for generating the positive key. So as you can see from the figure here that when we align the predictions of the queries and their augmented latent neighborhood using the contrastive loss, the samples will clusters in their latent space due to the pull and push effects of the positive and negative keys, respectively. And the observation is that the radius of the spherical Gaussian profile is actually determined by the sigma of the Gaussian noise. And when we increase the sigma, or when we increase the standard deviation, a larger radius will lead to a wider traverse of the augmentation, so that we can generate a wider range for the positive for the pull effect for the pull and push effects for the positive and negative keys. And then the contrastive loss will pull the features of the positive key closer to the feature of the Curie while pushing away those of the negative key. And the pull and push effect will actually widen the gap between the clusters as their augmentation traverse along the Gaussian profile. Therefore, when we have a large traverse regions for the Gaussian profile, we can have a wider gap between the clusters. So our conclusion is that when we have a larger standard deviation, we can have a wider gap between clusters. This is actually good for the classification. However, it also increases the risk of incorporating irrelevant features into the clusters. Therefore, here comes our questions, is that how can we determine the standard deviation? Recall the observation from the first few slides that by examining the t-SNE visualization of the target features when we extracted the features from the source pre-trained model, is that the neighboring target samples are still in the latent space are still share the same ground truth. This actually gives us a very simple solution, is that we can simply set the variance of the Gaussian noise for the latent augmentation traversal to the standard deviation of the source-informed latent KNNs. And next, we will talk about our empirical validations of our method. We first validate our method on a toy dataset called Moon dataset. So this dataset simulates domain shift by rotating data samples orientation, and each domain consists of an interleaving half circle with 1,000 data points, and the target domain replicates the structures with the 30-degree rotation around the mean of the source domain. And both domains include Gaussian noise with a standard deviation of 0.1 and are generated using the distinct random set. And the backbone network we use to validate this toy to do the validations on the toy dataset is simply a 5-layer MLP without any nonlinear activation. So as you can see from the results showing below here is that our CLAM can successfully derive a decision boundaries between the two domains. Next, we discuss our results on the benchmark dataset. The first experiment is the Office 31 dataset. This dataset consists of 4,652 images of 31 object classes captured from 3 domains, Amazon, Webcam, and DSLR. And the results is shown in Table 1. So as you can see from the Table 1 that with the simple InfoNCE-based contrastive objective with our empowered by our latent augmentation strategies, we achieve the state of the art on this data set. We also conduct experiments on the Office Home dataset, and in this dataset, we achieve the state of the art performance again. We also conduct experiments to validate our proposed CLAM on the large-scale dataset used for the 2017 ICCV Virtual DA challenges, the VISTA 2017 for classification dataset. And this dataset consists of 280K images of 12 object categories. The source domain contains synthetic images generated via the 3D model rendering, while the target domain consists of the real images captured by cameras. As you can see, even for the large-scale dataset, our proposed CLAM still achieves the state-of-the-art performance. Therefore, we conclude our work by summarize our contributions. First, we hypothesize that the domain shift causes a significant dispersion in the target features. However, the nearby points still tend to share the similar labels, which explains the success of contrastive clustering in source-free domain adaptation. Our second contribution is that our theoretical analysis of contrastive SFDA reveals three often overlooked factors, which is associated with the aforementioned hypothesis, have significant impact on the target classification performance. So based on these three oversights, we introduce our source-informed latent augmented neighborhood, a simple yet very effective latent augmentation technique explicitly designed to improve contrastive SFDA methods. And our fourth contribution is that we demonstrate through experiments that with the simple info NCE objective, our framework can achieve the state-of-the-art performance on the benchmark datasets, which support our theoretical findings. And we would like to thank for your interest in our work. And this work is supported by the NSERC Discovery funding. Thank you.